Welcome. Today, we're diving into the world of building management systems, or BMS. At its core, BMS architecture is all about how different devices, like sensors, controllers, and user interfaces, work together to control and monitor a building's environment. A well-designed BMS ensures everything runs smoothly, from heating and cooling to lighting and security. In this video, we'll break down the layered structure of a BMS, explore the roles of each component, and see how they communicate for efficient, reliable building management. Let's get started by understanding the big picture of BMS architecture and why it's so crucial for modern buildings. Typical BMS is structured into three main layers, each with a unique role. First, there's the field level, where sensors and actuators gather and act on real-world data. Next is the controller level, which processes this data and makes decisions. Finally, the supervisory level manages data, provides user interfaces, and stores information. This layered approach helps organize complex building systems, making them easier to manage, expand, and troubleshoot. As we move forward, we'll look at each layer in detail, starting with the field devices that sense and control the building's environment. At the field level, sensors and actuators are the eyes and hands of your BMS. Sensors measure things like temperature, humidity, pressure, and CO2, providing real-time data to the system. They come in analog and digital types, depending on the signal they send. Actuators, on the other hand, receive commands from controllers to operate equipment such as valves, dampers, or motors. They can be simple on-off devices or modulating for precise control. This layer is essential for gathering accurate information and executing physical changes in the building. Moving up to the controller level, we find direct digital controllers, or DDCs. These controllers receive data from field sensors and process it using programmed logic and sequences. They then send precise control signals to actuators, handling tasks like maintaining temperature, managing alarms, and running control loops. DDCs also communicate with each other using protocols like BMS, MSTP, or Modbus RTU, often sharing data across a network. This layer is the brain of the BMS, making real-time decisions to keep building systems running efficiently. The top is the supervisory level, where the BMS server and client workstations reside. The server acts as the central hub, storing data, managing alarms, and hosting dashboards and reports. Clients, like operator workstations or mobile apps, provide a user-friendly interface for monitoring, adjusting set points, and acknowledging alarms. This level ensures that building operators have the tools they need to oversee and control all aspects of the facility, whether they're on-site or remote. It's the command center that brings together all the information and control capabilities of the BMS. Let's visualize how these layers connect. At the bottom, field devices like sensors and actuators send analog or digital signals to DDC controllers. These controllers communicate over networks, such as RS-485 or Ethernet, often using BMS or Modbus protocols. The controllers link to an automation network switch or router, which then connects to the BMS server. Finally, client PCs, laptops, or tablets access the server for monitoring and control. This architecture ensures seamless data flow from the physical environment up to the operator's screen. Communication is key in BMS architecture. Different layers use different protocols to ensure reliable data exchange. Field devices use analog or digital I/O to talk to controllers. Controllers communicate with each other using BMS MSTP or Modbus RTU. For controller-server communication, BMS/IP and Modbus TCP/IP are common, while servers and clients often use web-based protocols like HTTP or HTTPS. Choosing the right protocol for each layer is essential for compatibility, speed, and security. BMS architectures can be centralized, distributed, or even cloud-based. In a centralized setup, all logic resides in the central server, and controllers act mainly as input-output devices. Distributed architectures, which are most common, allow local controllers to execute logic independently, improving reliability and scalability. Cloud-based BMS offers remote access and advanced analytics, leveraging cloud storage and processing. Each approach has its strengths, and the choice depends on the building's needs and complexity. Reliability and security are vital for any BMS. Redundancy features like dual power supplies, network failover, and server hot standby ensure the system keeps running even if something fails. Controller-level fallback logic helps maintain control during network outages. On the cybersecurity front, it's important to isolate the BMS network from the corporate IT network, use firewalls and VLANs, encrypt communications, and keep audit logs. These measures protect the building and its occupants from both technical failures and cyber threats. Wrap up, a robust BMS architecture is essential for seamless building operation. Understanding the roles of sensors, controllers, and servers, and how they communicate, helps in designing, implementing, and troubleshooting effective systems. Always consider scalability, security, and redundancy when planning a BMS. With the right architecture, you can ensure efficient, safe, and future-ready building management. Thanks for watching, and stay tuned for more insights into smart building technologies.